So in last class I have discussed about the theory of Fresnel's zone plate experiment. So today now I will demonstrate this experiment in our optics lab of Department of Physics of IIT Kharagpur. So this is the setup. This is the experimental setup for zone plate experiment. So this is basically zone plate. As I showed you, it is. So as I showed you, this is the zone plate. So that we have put on this holder. So this is the basically this zone plate is here on this holder. Now experiment is, as I told, that from source light will fall on the zone plate, and then from the zone plate basically alternate zones are blocked. Okay, half-period zones are blocked. So this will act as a convex lens, like convex lens but multifoci, means there will be multifocal length, means so light, if it is lens, so light in this other side, light will be focused at the focal length. So light will be focused at different point, means at different distance, okay, because it has different focal length. Okay, so that means there are two parts. One part is I want to put parallel rays on this zone plate. For that I need arrangement. Okay, and second part is that this light will so from the other side, so light will be focused at the focal length. So that focal length I want to find out, and focal length, whether the focal length are different, for focal length are different that we are expecting from our theory. So here we want to see whether multifocal length we get or not. So we have to if so, then we want to measure that focal length. Okay, focal length. Okay, and that focal length for different m. So this is the laser source. Generally, laser source gives monochromatic light and also parallel light. But there is a divergence of this light. But for this experiment, since we want to skip this distance of the object, so that's why we want to get the perfect parallel rays which will fall on the zone plate. So these three so this is the laser and this is the zone plate. Between these three holders are there. What are there in these holders? Actually, in this holder, these lens are there. Okay, here you can see it's the plus 20 millimeter. So here convex lens is there of 20 millimeter focal length, and then here you can see the minus 50 millimeter. So there is a concave lens of focal length minus 50 millimeter, and this is another lens, convex lens, this plus 100 millimeter. So that is the focal length of convex lens. So here these three lens, combination of three lens, keeping uh, keeping keeping a different, keeping at a particular separation of among the or between the lenses, okay, will give the parallel rays, parallel rays which will fall on the zone plate. Okay, so to understand that one, so I think this I will show you. It will be easy for you to understand if I show this diagram. So here you can see this laser. Okay, it's a laser. So this is this laser. So I can show like this. So this laser, okay, then this is a lens of 20 millimeters or 2 centimeters plus 2 centimeter focal length, convex lens, and then this is 50 millimeters, minus 50 millimeter, minus 5 centimeter, this convex concave lens, and this is 100 millimeters. So this is the L3, and this that or plus 10 centimeter convex lens. Okay, and they are placed at, if this laser source, so we have a scale, so laser source we have put at 0. Okay, on this scale we have put at 0, laser source we have put at 0. Okay, this holder. So and then L1, this is L1, it is put at 15.6 centimeters, then L2 21.2 centimeters. So difference between these two you can find out, it will be I think 5.6. It take difference, so this separation is 5.6 and this one is put at 29.7. So there is a separation, so it will be I think 8.5. Okay, so this combination or this separation, okay, of these lenses having the focal length mentioned here, okay, will give basically parallel rays, on the other side of the L3. So here then we have zone plate. Now on zone plate, these parallel rays are falling, as if this light is coming from the infinity. So A is 0, right? Now this part, okay, this arrangement is for parallel rays falling on the zone plate. Now you see here, I can show you. So what will happen on zone plate? So light are falling on the zone plate. So then there will be diffraction, okay, and then we will get diffraction pattern on the other side. Okay. So can I have a white paper? White paper. So I will. Okay. So other side will get basically, you see, other side will get, you see, this some spot you are seeing at the center, there's some spot you are seeing at the center, but it's very difficult to see that one, Okay, you are getting some pattern at the center. At the center, you are getting getting spot. It's a high intensity spot you are getting. Intense spot you are getting. Okay, not everywhere very intense. You see here is looks very intense. If I go further away, if I go further away, so you see here is very intense. Okay, if I go further, it's again so. So we are getting intense light. So this intense light is basically intense light at the center. Okay, so that most of the light are focused on the focused at the center, and also this, as I told that on the screen basically we'll get the diffraction pattern. Okay. And that diffraction pattern will be basically dark bright, this kind of circle. Okay, but here our interest is to find out the focal point of the zone plate. Okay, and focal point will be at different distance. So that we want to find out. Okay, so what is the focal point of this or focal length of the zone plate, and that focal length we have many focal length that we want to find out. So this can be here, one is here, another is here, third one is here, fourth one I don't know. Okay, that I want to find out. Okay, so that means I want to find out this B value or V value. Okay, 1 by A plus 1 by B or 1 by U plus 1 by V. Okay, so source distance is at infinity. Okay, and then I want to find out this skin distance. Okay, that will be the, if I can locate the position where the beam are concentrated at the center, so then that will be the focal point, and corresponding length will be focal length. Okay, so it is somewhere in this range, it will be there, and there will be multifocal length, multi position. So you just think for one position. Okay, now what we'll do, we'll take help of convex lens, another convex lens. So of its the focal length is 50 millimeter plus 50 millimeter, focal length is plus 50 millimeter. Now what we want to do is that, so light is so what is happening? So here you can see that so far I have discussed that parallel rays are falling on this zone plate. So after zone plate, so after diffraction, okay, so there will be, since it is multifoci, so at different distance, okay, so light will be focused at different points. Okay, so this will be one focal point, this is another, this is another, this is another. Okay, it may be first one, second, third, fourth, or other way, I don't know, that we have to see. So now so that I have to find out, so then we can tell that zone plate and this one of them. Okay, so that distance will be basically B, so BM, and that is nothing but the FM, okay, for zone plate. Okay, so now we are taking help of another convex lens having the plus 5 centimeters the focal length. Now what we'll do, we'll search for different this. So this will act as a source for this this one, okay, point source for this one. So this light will come, okay, and it will make it parallel, okay, by this lens, and that will fall on the screen. That screen is there. So here basically what will happen, so this lens will help us to whatever here, whatever the here is the pattern is formed, that pattern, this will be put on the, this pattern will be put on the screen, okay. So with the help of this fourth lens, we'll get the image, okay, whatever at this point in this region, so that will get on the screen, okay. So in that case, so we can say that this is the, so this is the object for this lens. So this is basically, we can say this is the basically U, okay, for this lens, and then this screen, that where we are seeing the image, it's a larger distance. So that is basically V, okay. So 1 by U plus 1 by E equal to 1 by F minus 1 by V. So so distance between the skin and lens, that experimentally we can measure, okay, and corresponding U we will find out. Now this U is nothing but, BM, and that, okay, no, we will find out the U. Now when we will find out U, now if I know the position of the zone plate, so this side is not disturbed. If I know the position of this one, okay, so difference between this L4 and zone plate, difference between the L4 and zone plate, that position, so that will give this distance, okay, minus U minus UM for different order, minus UM will give you this BM or FM. It will give you BM or FM, okay. So basically we have to shift the L4 lens, okay, and find out the high intense center, high intensity at the center of this pattern on the skin, okay. And then for that position we have to note down this, for position of the L4, and zone plate position is known, screen position is known, okay. So if I know the L4 position, then here from this relation you know the F for this lens for L4, that focal length is known to you, and we will get also, yeah, V basically from this reading you will get. So U is used here, okay. So ultimately we have to record the reading M versus FM, okay, M versus FM, okay. Then after the reading we can, as I mentioned, that we can plot 1 by M versus F, 1 by M versus F, and from the slope you will get, one can find out the radius of the Fresnel subzone, okay. So just here you see, now I think, so parallel rays are coming, so we have to note down for this reading, as I already note down here, okay. So you have this data, okay. So these are fixed, and that we cannot disturb them, because then only we will get, one can calculate and see, only you will get the parallel rays. Okay. Now what? So actually you can find out, you see this, now what happened, this focal length, now this, I think one more I should show you. Yes, now these multifoci points are there, multifoci points are there, that points are the object for this lens. Okay, object for this lens. So it will be on at many places. Okay. So now if I start from this side, so I will, so here what we want to see, as I told, that we have to get concentrated intensity at the center. So let me, I start from this at the end. No, so I am changing and you check it. The center one has to be very intense one. Yes, I am getting almost, yes, you can see. Okay. Yes. Okay. So we have to take reading of this L4. We have to take reading of this L4. Okay. Then you can calculate FM. Okay. So here this one probably M equal to 1. Okay. So next I am going ahead. and then I have to find the next position. Yes, 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 yes. You can see this for the second order, M equal to 2. Okay. Then you go ahead. It's now very close things, sir. So very slowly I have to go. You see now this is the M equal to this third one. Okay. So take reading of this L4. Okay. Then that way you take few more, you can find out few more. Okay, so the one has to adjust slightly and find out. This is the for M equal to 4. So this way just you have to take just reading of the L4 lens. Okay, and you can find out. You can calculate the FM. Okay, for different order. Now you plot, as I told, 1 by m versus FM. Okay, 1 by m versus FM, and from slope we can find out the radius of the zones. Okay, so and you can then just compare with the theoretical value. Sm should be square root of m. Okay, so that is the experiment. This is the, I think, beautiful experiment is a very good example for the Fresnel's diffraction. So I will stop here. Thank you for your attention.